Today we are going to continue talking about some of the discrete choice or discrete outcome models that we've been talking about previously. So as an example, the binary and multinomial logit and probit models are examples of discrete choice or discrete outcome models where our dependent variable is nominal in nature and not continuous. So it's discrete essentially, as the names imply there. And so we'll talk about a different class of those same types of models today when we refer to ordered probability models. And so that's where we're going. And so we'll start with just an introduction overview of what ordered probability models are. We'll talk a little bit about advantages or disadvantages all as compared to different alternate approaches. And then we'll work through a case study using data from a Michigan DOT research project we had conducted about a decade ago. And then over the remainder of the semester, we're going to have a little switch in terms of format. So my plan on the Mondays will be to deliver the new content in terms of modeling approaches and so forth. And then Wednesday will be a combination of research presentations, so basically examples of these methods we've talked about being applied in different contextual settings, and then project working sessions. So if any of you have questions, those would be opportune times. And then even today, if any of you have questions that are project related, I'm happy to answer any of those because we'll probably find that some of the other students are having some of those same questions. And I'm going to close the door if that dog is going to be barking. Apologies again. Okay. So when we talk about discrete outcome models in transportation, we've worked with a few data sets up to this point. Oh, no, the other dog's crying. It's fine. Sorry, thunderstorms in Okemos. The dogs are a little unnerved. Okay. And so, as I had mentioned, we've worked with a variety of different types of data sets where our dependent variable is discrete in nature. And so, oftentimes in various settings within transportation research, we'll run into discrete data that have some inherent natural ordering structure, as opposed to like the route choice example we talked about last week, where there wasn't necessarily any sort of inherent numbering structure or meaning to the way those variables were coded in terms of which of the routes were selected. In contrast, when we look at the transportation literature, there are various different settings where this comes into play, with one of the most common being survey data as an example. So we can have questions as to whether or not you strongly agree, or neutral, disagree, or strongly disagree as an example. So we talk about that as a 5-point Likert scale that expresses how people align their views with any question or statement of interest. We have rating scales, so individuals can be asked to rate anything and everything on various scales. And then we have other types of data, like if we talked a little bit previously about crash data, where when a crash occurs, the injuries sustained as a result of that crash can be classified into a series of discrete categories. And there's a natural ordering to those categories in that a fatal injury is more severe than a minor or major injury, which is more severe than a no injury or property damage only crash. And so in these settings, we can use some of the other families of models that we've talked about previously in the semester, but there are a few limitations and costs associated with the application of this. And so that essentially provides us with motivation for the use of ordered probability models. And so to demonstrate this, we're going to work with some case study data from a Michigan DOT study that was focused on public perceptions of roundabouts. And so as a part of this study, we basically selected and implemented a web-based survey to get road user feedback as to roundabouts. So whether they liked them, didn't like them, if they had concerns, whether those concerns related to safety or operational characteristics, the frequency in which they use those roundabouts, et cetera. And so ultimately we had a sample of nearly 12,000 respondents. And so that's the data we'll be working with as a part of today's course. Those same data are available on the D2L site in this week's material if any of you are interested in following along as we work through some of the examples here, okay? And so ultimately, our intent with this survey was to understand the concerns of road users and to help MDOT understand ways that they could effectively mitigate some of these concerns and alleviate some of the issues that arise when they plan on implementing a roundabout in a community. And so just as a little bit of context, typically when roundabouts are introduced, there may be some degree of pushback, and it may be significant pushback early on, and a lot of that relates just to driver familiarity. And generally speaking, people don't like new things in many settings, and that's particularly true for transportation projects. But what the literature tends to show is that over time, the public becomes more accommodating and accepting of roundabouts. And so what we see here is basically a data dictionary as to the different characteristics we're using here to try to assess that public feedback of roundabouts. And so our three primary variables of interest are down at the bottom here, and that's basically asking the public how they feel about the safety and operational characteristics of roundabouts. So do they believe that roundabouts are less safe, equally safe, or more safe as compared to traditional, i.e. signalized or stop controlled intersections? And similarly, do they believe that roundabouts are more, less, or equally efficient to traditional types of intersection control? And then based on that, just general feedback as to whether or not the general public is strongly in favor of or strongly against the use of roundabouts. And so when we think about the differences we might observe between individuals, we were interested in locational factors. So as an example, we've got a series of indicator variables here that are specific to each of the MDOT regions. We also had a limited number of responses that were either outside the state of Michigan or from unknown locations. Age and sex are two categories that have generally shown divergence of public opinion on many issues, and so we collected that information here as well as a variety of different questions that sought to understand how frequently and in what capacity road users actually had traversed through roundabouts. So whether they use them as an automobile driver, as a bicyclist, motorcyclist, and so forth and so on. We ask how frequently they use roundabouts. So if they used one today, in the past week, past month, etc. The number of roundabouts they'd driven outside of the state of Michigan as well as within the state of Michigan. So at the time of this study, they were still relatively novel in nature. We also asked whether any drivers had purposefully avoided roundabouts. So there are certain groups, particularly there's been research that's shown that older road users are less comfortable generally with roundabouts. And then we also asked about general rules of the road and how many people knew whether or not the traffic that was entering the roundabout had to yield or the traffic that was already circulating. And so that gives you some big picture context there. We'll work through this in a little greater detail over the remainder of today's lecture, but that gives us a backdrop. And so if we look at some of these data, the operational and safety questions, so generally speaking, the public found them to be significantly more efficient, but also significantly less safe. And so you'll see it's basically a balanced split there. 52.7% thought they were significantly more efficient and significantly less safe. And then somewhat of a mix between those that were in between and or felt that they were less efficient and or more safe. And then that information taken in combination with the other factors gives us information as to this general distribution you see right here. And so this is kind of interesting. So if you think about trying to analyze survey data in this nature, it's somewhat interesting because in this case, we don't really see a persistent trend here. It's really bimodal in nature. So you tend to have one group that's very strongly in opposition, one group that's very strongly in favor, and then you have a number of other groups that are essentially in the middle there. And so if we think about this, if we try to apply our general starting point of an ordinary least squares regression model, there'll be a few reasons why we might run into concerns there. Multinomial logits would represent another alternative. So we could basically zero out one of these categories and estimate some utility functions for each of the others. to discern differences in some of these parameters. But in any case, we're going to talk today about what some of the drawbacks and limitations of various approaches are, and then that'll lead into ordered probability models. Okay. And so we talked a little bit, or quite a bit previously, about ordinary least squares. And so as we think about that, can anybody think of some concerns that might arise if we were to use an OLS framework for the analysis of the types of data we're looking at here? And hold on, I'm going to try to walk a tightrope as we do this. So as I solicit responses from the audience, I'm going to go into remote desktop, and we'll actually demonstrate what happens if we try to use OLS. But does anybody have any thoughts as to what some problems may be if we try to use OLS when analyzing survey data that's on a 5-point scale, as we see right here? I realize it's Monday morning. Okay, so let's...
Oh, Dr. S, it could still predict values that are like less than 1 or greater than 5, and that wouldn't make sense in this context.
Yeah, so very similar to the stop-go scenario that we had started with in a binary logit case. In this instance, you could definitely predict values that are significantly outside that primary range of interest. And so I'm just going to now, I guess, first of all, to verify, can you all see my screen right now?
Yep.
Okay, great. So if we were to estimate a linear regression model for just that overall satisfaction, which again is coded 1 through 5, and we'll just start nice and simple here. We'll include age and gender, and let's just do that as a starting point here, and we'll save our predicted values and residuals. And then we'll also include our histograms and normal probability plots. Okay, and so we run that analysis. And so first and foremost, if we look at our residuals, does the normality assumption appear very good in this case? Clearly not, right? Because what's tending to happen here, and if you think about the nature of the data, you have a lot of people that are very strongly on either extreme there. And so consequently, we see this interesting pattern here, and that's also reflected in this normal probability plot we see down here. So we see significant divergence from that normality assumption. Now, if we go into our chart builder, and we're going to create a scatter plot again of our residuals versus our predicted values. And so you notice that same type of trend that we had experienced previously, right? So we're basically truncated on either extreme. So those residuals can only be so large or so small. And when you're at either extreme, those residuals will tend to be either very large or very small in relative terms. And so obviously in looking at this, we can tell then that our residuals are going to be a function of our predicted values, and similarly will also be correlated with our predictor variables of interest, okay? So obviously there are some concerns here. And then back to the point that Jordan had raised, if we look at the predicted values, we're not actually going to see anything outside of the range here as I scroll down. But this actually highlights another of the concerns here, is that virtually all of your predicted values here are going to be between categories 2 and 3 or 2 and 4, as the case may be. Okay. And so if we think about that, then from just an interpretation perspective, well, what are we actually getting as an outcome there? Because interpretation tends to become very problematic, okay? And so consequently then in that OLS framework, we're assuming that Y is measured on an interval scale. And so in this case, that's obviously not the case. We've got those 5 categories, and so that introduces a series of violations of our underlying regression assumptions. And then, as I had alluded to, there's just some concerns with interpretation and interpretability there. We could look at these data using a multinomial logit model. And so I guess let's have fun today. We'll jump back into remote desktop here real quick, and we can replicate that same procedure here. Oh. Okay, can you see my screen again?
Yep.
Okay, sorry, I had two remote desktop windows, so I wanted to make sure I wasn't sharing the wrong one. And so I'm just going to quickly show a multinomial logit model specified in the same manner as we saw previously. So we'll look at overall satisfaction versus age and sex. And so in this case, this is a viable approach. And so if we think about this in concept, this would be a reasonable way to proceed. Now, one concern that arises, and one of the advantages with the ordered probability models as compared to the multinomial probability models, is that the ordered models make more efficient use of the data. And that, well, you'll understand what I mean by that in a few minutes here. But if we think about this in the case of a 5 outcome case here, for each variable of interest in a multinomial framework, we would basically estimate k minus 1, or the number of categories minus 1, different utility functions. And so it tends to be somewhat expensive in terms of computation, in terms of the number of observations we need. So in this case, we have just the two variables, but those two variables would require the estimation of 8 parameters, right? And so particularly as our number of alternatives gets larger, multinomial models become somewhat less attractive to us from an analytical standpoint, okay? And so we'll pull it back into the PowerPoint here one more time. Okay, and so in the multinomial case, one of the big factors and limitations here is that you're basically ignoring the ordinal nature of the data. So in the case of the survey data, we know that strongly agree is greater than agree, which is greater than being neutral, and so forth and so on. So there's a natural and inherent ordering process there, but we're losing sight of that fact, and as a consequence, we're estimating a significantly larger number of parameters than we might have to otherwise. And so ordinal probability models, or ordered probability models, represent a very promising way of trying to work around those specific concerns that we have, okay? And so just to recap quickly, when we talk about those multinomial probability models that were introduced previously, the way those work in concept is that we're estimating separate utility functions for each of those individual levels that dependent variable may take. We arbitrarily zero out one of those categories, and then we make some assumption in terms of what that underlying distribution for the error terms would be, which would result in either the multinomial logit or probit model as an example, okay? Now, in the ordered probability setting, we approach things somewhat similarly, but from a slightly different perspective. And so what we're going to do at the onset is we're going to define a latent variable of interest, okay? And so in this case, we'll say that's general public satisfaction with roundabouts as an example. So that's not something that we know per se. It's somewhat abstract, but we are basically observing this a variant of this variable through that survey question that we're asking, okay? So what we're trying to get at is the general level of public satisfaction through that survey question. And so we can assume that that latent variable is going to be a function of some series of predictor variables, and we're interested in estimating what the parameters or the effects of those predictor variables are on that underlying variable of interest, okay? Now, to operationalize the model as we've done in other settings, we need to make some assumption as to how that error term is distributed. And as in the multinomial case, we can basically either assume that it's distributed as logistic in the case of the ordered logit model, or as standard normal in the case of the ordered probit model, okay? And so from there, then we know that in our case, that yi variable that we're observing from the survey data can take one of 5 different values. And so what we're trying to do is basically think about that probability density, that probability distribution function, And we're trying to establish where cut points are located, depending upon what portion of that sample we're looking at. And that'll become more evident as we look at some of the graphics on the subsequent slides here. So if we think about this in concept, we're basically defining threshold values on a probability distribution. And so those threshold values are basically breaking that distribution into a series of intervals that when we sum across the intervals, that would represent 100% of our sample or our population. And so ultimately, we're trying to determine what the threshold values are that would help us to reflect the actual shares of the population that fall into each of those 5 categories, okay? And so if we think about these 5 different values that y can take, y equal to 1 would be the left side of that distribution, y equal to 5 would be the right side of that distribution, and obviously the intermediate values 1, 2, 3, and 4 would fall in between. And so what we're going to do, we're going to assume that that lower threshold is negative infinity. And so basically we can calculate the probability of us observing a survey response of 1 as just the probability of that latent variable that we've defined or estimating from the equation being less than some threshold value. And so these mu's are similar to the betas. These are parameters that we're looking to estimate ultimately as a part of our model, okay? And so that equation then basically simplifies to what we have right here. And then we introduce the fact that this yi latent variable is a linear function of some combination of x's and betas and then some underlying error term. And so from that, we can simply rearrange this equation from the underlying algebra. And once we've made an assumption as to the distribution of these error terms, we can then arrive at an estimable function here. And so we're basically taking that first threshold and we're subtracting off whatever that linear in parameters function yi star is equal to, okay? And so once we make an assumption as to the distribution of that error term, it's simply a matter of us calculating for that model and the given parameters, evaluating this probability expression, okay? And this will become a little bit more evident on the subsequent slide where we work through what this actually looks like in practice. But continuing on, if we think about the probability of an individual selecting option 2, which in this case, option 1, if you'll recall, was strongly opposing roundabouts, option 2 was slightly opposing roundabouts. And so just extending the same example we saw previously, the only real difference here is now we want to determine 2 threshold values. So we're estimating the threshold that separates category 1 from category 2, and also the second threshold that separates category 2 from category 3, okay? And so then at the end of the day, we're evaluating the differences between these 2 cumulative distribution functions. So the threshold minus the corresponding linear and parameters regression equation, okay? And we can continue on, and in the final case for our largest category, category M, it would just be 1 minus the cumulative distribution function of that highest threshold. So if we have 5 categories, we would need 4 thresholds in order to separate those categories, okay? And this should make a lot more sense if I'm remembering my sequence of slides with what you see right here, okay? So from a modeling perspective, this is basically showing us, you can think about this conceptually as a distribution of our data ultimately, okay? And so we have these thresholds and we're ultimately interested in determining where these thresholds lie, okay? So in the simplest form, if we were to estimate a constant only model in that setting, we won't have any x's or betas to be concerned with. We would just be estimating these parameters, mu1, mu2, mu3, and mu4, okay? And so those would then separate basically what percentage of our data fell into each of those 5 response categories we see indicated here, okay? And then as we add variables to our model, those are going to shift these thresholds in one direction or another, okay? And so you'll notice here on the preceding slide, the way this is structured, you take the thresholds and you're subtracting off that linear function here. So what that means is if we have a parameter that has a positive coefficient as an example, so something that's increasing the favorability of roundabouts in this setting. That would tend to make this right side term here larger, which would shift each of these thresholds to the left, right? And so positive coefficients would make it more likely that someone would strongly support roundabouts and less likely that someone would strongly oppose roundabouts. In contrast, if we had a negative coefficient beta for any given parameter, that would have the opposite effect here. So we would be shifting the parameters in this direction to the right rather than to the left. And we would make the lowest ordered response more likely and the highest ordered response less likely as a consequence there, okay? Now, the probabilities in the interior categories is going to vary quite a bit. And so from a big picture perspective, what we're doing in the ordered probability models is we're shifting all of these thresholds by that same amount, x times beta, where again, this is just basically a series of matrices, okay? So hopefully that makes sense as we continue on here. And so what we're doing in concept then, you can think of it as though we're setting a series of parallel logistic regression or probit models to those cumulative probability functions, okay? So the probability of y being equal to any specific value would just correspond to the differences in the cumulative distribution functions between that upper threshold and that lower threshold that separate that category from the adjacent categories, okay? And obviously for the lowest category, that lower threshold is negative infinity. And for the highest category, that highest threshold is basically positive infinity, okay? And so as indicated previously, what those functions are doing then are basically shifting these thresholds, these cut points, and they're helping us to understand what the nature of the relationship is between our predictor variables of interest and how likely it is an individual would fall into any of these specific categories. All right. And so there are basically two different assumptions we can make in terms of that error term. The first of these is we assume that it follows the standard normal distribution, in which case we're just calculating the cumulative standard normal density function for each of those threshold values while accounting for the effects of those variables of interest. Or in the alternate case, the ordered logit model results when we assume that those data follow the cumulative logistic distribution function here. And so in this case, we're just basically taking the exponential over of this quantity divided by 1 plus the exponential of that quantity, okay? And that's how that cumulative logistic distribution function is applied, okay? And so one general issue here, interpretation is somewhat less straightforward as compared to some of the other family of models that we've looked at previously. And that largely relates to these interior categories. And so I had mentioned this point previously, but if we have a variable with a positive coefficient, we know in all circumstances that's going to mean that this area at the top is going to become larger and the area at the bottom is going to become smaller. The converse is true if a parameter estimate is negative, but the interior categories here require a little bit of additional calculation in order to understand whether or not a positive or negative beta is going to increase the likelihood of somebody falling in the category 2 or 3 or 4 as the case may be, okay? And again, we're assuming that these thresholds are all shifted by the same amount. There are some more flexible families of models that relax those assumptions. In the most extreme case, we could look at a multinomial model. But again, keep in mind in that case, we're going to have to estimate multiple. So in this case, 4 times the number of parameters we would, nearly 4 times the number of parameters as we'd see in the ordered probability models, as will become evident in a few minutes here, okay? And so to that end, just to kind of walk you through how this works functionally here. Here is basically some SPSS output, and this shows the number of individuals that fall into each of those 5 categories. So as you may recall, a larger percentage of the sample tended to be against roundabouts versus in favor. And so that was roughly 39.4% of the sample. In contrast, 30.9% of the sample was very strongly in favor, okay? And then you see the intermediate probabilities here as well as details of the missing values and so forth and so on. Now, the simplest model we can estimate here is a model that includes only those thresholds, okay? And so this basically shows us what the corresponding values are, again, in a logistic or logit framework for each of those 4 thresholds that separate our 5 categories of data, okay? And so these are our corresponding thresholds, mu1 to mu4. And as you can see up here, if we apply and calculate the cumulative logistic distribution function here for that first threshold, that exactly matches that 39.4% we see right here. Likewise, as we look at the probability of somebody opposing, being neutral, slightly in favor, and strongly in favor, those probabilities also exactly match as we see right here, okay? And so again, all this model is doing in the simplest case is just telling us where these thresholds lie, okay? Now we can take the same approach here, and we can consider the effects of some predictor variable of interest. So in this case, I've added the variable female to our model, okay? And as I had indicated previously, within the way we've set up our data here, a positive coefficient means that specific observation, that individual in this case, is more in favor of roundabouts, and a negative coefficient means that they're less in favor. And so as we see in this case, we find that females tend to like roundabouts less than males for whatever reason. I dare not speculate as to what the actual reasons for that are. But then as we look at the changes in the probability distributions here, all I'm doing here, you'll notice I'm plugging in those corresponding thresholds. So if I want to determine the probability of a male respondent indicating any of those 5 preference levels, all we would need to do is evaluate that cumulative logistic distribution function for those corresponding threshold values, okay? In the case of a female, what we're doing is we're taking those same threshold values and we're subtracting off beta x, okay? Now in this case, since beta x is negative, we're adding 0.805 to each of those corresponding thresholds, okay? So apologies, it was difficult for me to fit in the intermediate calculations here, but that minus 0.009 is just basically taking the minus 0.814 plus minus 0.805, okay? Likewise, for each of the other categories, you see those responses as indicated here. And then you can see there are some pronounced differences between the groups. So males, we saw roughly a 30.7% chance that they would strongly oppose roundabouts, whereas that was 49.6% in the case of females. And at the other extreme, strong support for roundabouts was significantly higher at 38.4% for males versus only 10% for females, okay? And so that's demonstrating results with the ordered logit. We can work through those same calculations with the ordered probit. You'll notice here we do see some rescaling with respect to these variables. So these aren't quite as large in magnitude as we would see previously. And as you may or may not recall from last week, the reason for that is that the logit and the probit models show very similar trends overall. And so the only substantive difference is that those parameters are basically rescaled. But if we take that information and we calculate the cumulative standard normal density values, those probabilities, as in the logit case, are going to exactly match the underlying data as you see right here. At least for the case where we have no predictor variables included, okay? Now we'll revisit the same example if we consider the effects of gender in this case. You'll notice these parameters have now been rescaled to a degree, and so that female parameter, instead of being minus 0.8, is going to be minus 0.5. And just as a general rule of thumb, that rescaling is roughly 1.6. So you'll tend to see the same differences in terms of the direction of effects of these parameters. And the choice between logit versus probit is almost entirely arbitrary in nature. There have been a number of research studies, and none of them really show a consistent preference for one framework versus the other. And so, again, it's just completely arbitrary here. When we look at the end results, these tend to be quite similar. There are some minor differences, so the probabilities aren't exact matches here. And again, that partially is due to the fact that these distributions are not identical. There are some differences, particularly in the tails of those distributions. But we see the same general trends here, in that support is tending to be significantly stronger among males and significantly weaker among females. But you will notice the magnitude of these differences are a bit different than we had seen in the LOGIT case. Okay, so they won't be identical unless we're in the very simplistic case where we're only estimating the thresholds. Okay. One concern that arises here, and I won't delve too much into this, is we're making an underlying assumption that the effects of those variables result in the same shifts in each of those 4 threshold values. Okay, so basically we can think about that as though the slopes with respect to each of those individual logistic or cumulative normal distribution functions is going to be identical or just shifted over by the same amount. Okay. Now, in practice, we can evaluate this assumption, and oftentimes we may find that that doesn't exactly hold, in which case that would provide some evidence that maybe we should consider a multinomial logit model or a multinomial probit model as compared to the ordered probability models as alternatives. And so keep in mind, when doing that, we are running into the issue that we'd have to estimate a significantly larger number of parameters in that case. And as in the choice between probit and logit, there isn't any sort of motherhood test that we can conduct that would tell us that, well, the ordered model is better here or the multinomial model is better here. So it's like a lot of the stuff we've run into in regression, it's part art and part science and working with these data. But that's one test that can be used to help to distinguish as to whether or not it may make sense to look at the multinomial model as a contrast. So if you think about the multinomial, the big difference there is that those thresholds aren't necessarily all shifting in the same direction, right? So some of them may shift in opposing directions. So maybe let's think about the survey data. We didn't have this information here, but maybe like political affiliation. So if you were a moderate, maybe there'd be a case where you'd be less likely to be in either of those extremes, in which case an ordered probability model wouldn't be able to pick up on that type of nuance in the data ultimately. Okay. All right. And so with that, I wanted to turn things over to just some demonstration and give us a chance to play around with the data set a little bit here. But outside of that, we will come back. Our next new content lecture next week will be on count data models. But like I said, on Wednesday, I'll go through and present some examples of applying different types of methods we've talked about in class to different data sets, and that will hopefully help you think through some of the analysis you're working on now for your own specific projects. And then we do have a deadline tentatively of next Sunday for preliminary results. And all I'm looking for here is basically high-level results from your model and where your analysis is heading. So just a few PowerPoint slides that would detail your progress to date. And this is largely just a check to make sure that you're kind of online and on track to wrap up the project in time. And we'll be coming together with some more examples and more discussion of that moving forward. But with that, I can turn things over to an SPSS demo. But before doing that, do I have questions from anybody about anything course related at this point? Okay, so if not, let me reshare remote desktop real quick. Okay, and so in this case, if we want to estimate an ordinal model, we go under the Analyze Regression pull down, and you'll see the ordinal family models right here. And so you'll notice I've already done a little bit of advanced work here. And so our dependent variable of interest here is that overall satisfaction with roundabouts. I've included female, sex, and age of the respondent here as categories. Now you'll notice here, if you click on options, this is basically going to give you some details, the top of which just relate to model convergence. So I would suggest you don't mess around with this. This is just setting bounds on the algorithm it uses for the maximum likelihood estimation here. But what we are interested in is the link function here. So this is basically what we're assuming in terms of the distribution of our error terms. So there are actually a few different alternatives we can consider beyond Probit and Logit. Those are very specialized cases that we won't get into as a part of this course, but by default, it will set this up as Logit, which tends to be the most widely applied to the ordered probability models, but you do have the option to estimate a Probit model here as well. In terms of model output, there are a bunch of different types of information that can be outputted here. You can save predicted values and probabilities, goodness of fit summaries, descriptive statistics. I have checked the box here for that parallel lines assumption just to demonstrate with this specific data set. And so we're going to hit continue. Okay. And then we have our model results. And so as in the other cases, we'll start with a summary table that just gives us details. I would suggest you work through this because this helps you to understand if there are any issues with missing data or observations being thrown out. So you'll see in this case, there are 247 cases where either the respondent didn't provide an answer on that 1 through 5 scale, or their gender or age was unknown to us. As I had mentioned, these are calculated using maximum likelihood, and so you'll see our log likelihood values here. So this is basically likelihood ratio statistics that are comparing an intercept-only model to our final model. And so this chi-squared variable you see right here is just the improvement in that log likelihood times 2, as you've seen previously. And our corresponding degree of freedom is just the number of parameters beyond the constant terms or beyond the threshold value. So in this case, we've had 2 predictor variables. And that's a very significant improvement in goodness of fit, which means that it looks like both age and gender do appear to have an influence here. We see some model output. So as in the case of the multinomial models, we can calculate a pseudo R-squared. Again, this is only useful for comparing competing models on the same data set. So an R-squared of 0.058, if you were to say this is a poor fitting model, I would cringe and I might get angry depending on the day there. But that's just telling us, in this case, there's a lot of variability in the data set. So if we're just considering a person's age and gender, we're not able to explain a ton of the information about their general perception of roundabouts as a consequence there. But when we look at the individual variables themselves, these are all very highly significant. So we're definitely picking up on some underlying relationships in the data here, regardless of what the absolute magnitude of those pseudo R-squared values are. Okay. And then interestingly, the parallel lines assumption here. And so what's happened here basically is this is a test that's simply comparing the model as specified here versus a series of competing models where we'd estimate separate logistic regression models for each category. So again, it's essentially a sort of comparison for the multinomial versus ordered. And so in this case, large chi-squared statistics are bad in essence. And so this means that we do see some issues with that parallel lines assumption. And so what that means, if we look at the differences between males and females or based on different ages, we don't necessarily see consistent changes in where each of those 4 thresholds are located. So in some groups, if we look across different age levels, we may see larger or smaller shifts between some of those categories than in others. Same thing when comparing males versus females. Now, from a big picture perspective, we do find, as mentioned previously, females tend to be less in favor of roundabouts than males, and we also find that older respondents tend to be less in favor of roundabouts as compared to younger respondents, okay? And so we could continue to work through various different formulations of these models, and so I would encourage you to do so. And I guess let's just think about who may or may not like roundabouts. And it's been a while since I've worked with this data, but let's assume that people in the northern part of the state, they're a little bit different in several respects. And so we'll check North and Superior region. We might expect that pedestrians would have different views on roundabouts because it's somewhat more challenging for pedestrians to navigate roundabouts. And then we can also look at, let's say, the frequency with which they've used roundabouts in Michigan. So maybe the more roundabouts they've used, the more comfortable they are with them and the more supportive. Okay. And so we'll hit OK here. We'll scroll down and look at our parameter estimates. And so I guess my intuition was correct in some perspectives here. So a few points of interest here. So when we look at these parameter estimates, we'll see that this threshold is not significantly different from 0 in this case. And so as we think about integrating those cumulative standard normal functions, as in the case of any model, we're going to always estimate this full set of thresholds, just like I would encourage you to always include a constant term. And so I just wanted to indicate here what the meaning of this parameter. So this is just simply saying that this isn't significantly different from 0. So that cut point is roughly in the range of 0. In this case, on that cumulative logistic distribution function, if we estimated a probit model, we might see the same thing regarding the standard normal. The other variables of interest, we see that females and older respondents, again, are less in favor. We also see that persons who are further up in the northern part of the state, specifically the Superior region and the North region, tend to be less in favor of roundabouts. That difference was not significant in the case of the North region, but the people in the Upper Peninsula are definitely seeing lower favorability. I was surprised when we had conducted the study. We actually see that pedestrians are more in favor of roundabouts versus other types of intersections. I'm not entirely sure what's being picked up by that specific finding there. And then we do find that as people have driven through more roundabouts, they do tend to be more strongly in favor of them as well, as what's being picked up in the last point here. Okay. Now that's one where I've thought about this, and even when we went through the analysis, I was wondering, well, is there some endogeneity at play there? So are the people driving through more roundabouts because they like them more? And that could be an option here, and that very quickly sends us down a rabbit hole here. But I think you can also make the argument that can be thought of as a one-way versus a two-way or circular relationship there. And I guess that was great timing, because just as I wrapped up my thought, my remote connection to my PC was lost. But that basically wraps up a quick introduction to ordered. Okay, I'm back. Can anybody hear me?
Yeah, I can hear you now. It's only about the last 30 seconds, just the very tail end there.
Okay. So it looks like due to the weather, we're having internet issues, but by good fortune, I did basically wrap up all of my content, unless I trailed off at the very end there. But I was basically just talking through the model parameters, and those all tended to make sense, generally speaking. And so I was going to open it up for any questions that anyone had. I'm very curious to see what happens with the recording when we have the Zoom cut out like that midstream, but I guess we'll find out as I edit this later today. But with that, does anybody have questions on anything related either to ordered probability models, or to the course project, or to anything else course related? I guess even the homework assignment, if any of you are still working through that. Anybody have questions on anything?
Yeah, I have a question about the homework assignment.
Okay.
Yeah. So, the main thing that was just confusing me was that, the way you structure the question, there's supposed to be six segments for each. Six segments for each treatment. That's two baseline, two outgoing, and then two incoming, right? But there are some that don't have up to six.
Okay, so I will open up that data set real quick, because I know I should have probably had a little bit longer discussion on that last week when I introduced the assignment, because it was a little bit of a learning curve, and I did have a a few questions that had arose there. So let me just open up that Excel sheet real quick. Okay. Hello. Okay, now it's switching microphones on me. Can you hear me well again now? Sorry about all the
Yes.
technical issues. Okay. All right. So yeah, the way this was structured, in concept, you could have up to 24 observations for each individual. And so in the case of the first person here, and just walking through this, for each instance, there's a generic coding structure that talks about the subject number. So this was the first subject out of the many who participated in this study. We're then given information about their age group. And so that would include either younger drivers, middle-aged drivers, and older drivers, and then also whether or not that driver was male or female. And so you can use that information to create then a series of binary indicator variables. The next sequence of information details the specific scenarios or test cases that were evaluated here. And so again, those first 6 cases are just familiarization runs. So that's the case where somebody's getting into the driving simulator, they're learning how to use it. They may be overcoming their motion sickness or whatever the case may be. And so in those instances, there was no testing or evaluation that was included there. So you could have just deleted those and completely from your data set or filtered them out, whatever the case may be. And then in the other cases, there were generally a series of 6 different treatments that were conducted. And so those 6 treatments would include one of 3 different types of device uses. So we would have either, in the first case here, a handheld device. So they're actually holding the cell phone in their hand, and they would either be receiving a call, making a call, or they would just have the phone there and not be focusing at all their concentration on any discussion. They would just have the phone in their possession, okay? And the second case denoted here would be where we have a headset. And so in that case, you would have someone who would have, similar to what I'm wearing right now with my AirPods. And so they would be talking on the phone, but they would have a headset used for those purposes. And then thirdly, we'd have the hands-free case where there's actually a phone interface built into the vehicle, okay? And so across each of those scenarios, and you have to go down to, I think, the very last lines of that very lengthy Word document data dictionary in terms of these structures here. But then these are basically broken up into groups where the first set, and these are just basically generated probably in a quasi-random nature. They're trying to randomize the sequence in which these events occur. But if you see an event between 301 and 305, that would be in the first sequence or first task. 306 to 310, or whatever the breakpoints were, would be the second set of numbers, and then the highest numbers would be the third interface. And so in this case, we know that during that first run, that driver is using a handheld device, and we go from baseline, which means no call is occurring, to outgoing call to incoming call, okay? And so the first 2 of these would be baseline cases. The second 2 would be outgoing calls. And the third set there would be incoming calls. Okay. And so if you're saying, are there cases where there are less than 6 then? Because that would be the only point
Yeah,
at which.
there are some cases where they are less than 6, like 30. I think run 30 has less than 6. Run 30.
Run 30. So when you say run 30, we're talking about subject 30?
Yeah,
or...
subject. Yeah, subject 30 is what I mean.
Okay. All right. So let's take a quick look here. Okay. So yeah,
I think the last.
Yeah, so there's only 24 cases there. So let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. So there's only
And
4
oh,
in that group. Okay. And so it looks like my presumption as to what happened here is we had 2 incoming, 2 baseline, and then for whatever reason they had to terminate the experiment. So either the person was sick, or they had to cease for some other reason. They had an equipment failure, whatever the case would be there. And so since we're still in that first and second range here, I can verify that these first 2 are incoming, the second 2 are baseline, and we're missing the outgoing in that specific case. Okay, so you'd have to actually match based upon these 3-digit categories at the very end to discern which of those would be missing. I recall there shouldn't be very many missing cases, but I know there were a few examples there. So does that answer your question, Falarin?
yeah. So I don't know if I can ask this question. My question is, should we remove this from data then, since they are not complete?
I don't want to do all the work, so how about we get some feedback on the audience, from the audience there. Did anybody deal with this in any particular way? So I guess, and this happens frequently in probability and statistics. So generally speaking, if we have missing data for a variable, we can't include that in our analysis because there's no way to incorporate that information. So as an example, if we use the velocity or distance when that signal goes from green to yellow, if one of those pieces of information is missing, we can't include that in the model. Now, in this case, the question is slightly different because we would normally have 18 observations from each of these individuals. And now the question is, well, if we can only include 16 in the model, should we do so? Or maybe your question is, instead of including 6, including just 4 of the 6, should we throw out these 4? So I guess I'm not sure if your question, Falarin, was to whether we should throw out these 4 or whether we should throw out all 16 of those cases there. But my suggestion would be to include them, generally speaking. You're still getting information from that individual that I think would be potentially useful to us. And generally speaking, I don't think there's a big risk there with any sort of issues being introduced. We're going to have a smaller sample in that one specific category, which in this case would be the outgoing call and the combination of outgoing with the headset specifically here. And so the only real repercussion of that is that you might have a slightly larger standard error for that parameter estimate. Or I guess if there was just something about this individual that was inherently a lot different, maybe that would be a concern. But the short answer to your question, I wouldn't have any particular concerns with keeping that in the model. Okay.
Okay.
But I typically would only suggest you remove data if there's a compelling reason to do so. So either some aspect of that data is missing, or for some reason you think that might be skewing our results here. And so it's tough to, and I apologize, you probably all get frustrated with how I give kind of squishy answers here. But there's not a clear-cut rule in terms of when or where you should omit specific variables or specific cases. It's, again, part art and part science. And so what I would suggest, if you have concerns as to whether or not these should be included, the easiest thing to do is run the analysis with those variables or those cases, run the analysis without them, and then see if you see any meaningful changes in the parameters. And if you don't, then it's probably fine to just include them in the larger data set. But if you do see some significant shifts, then that might give you a little bit of cause for concern there. Okay, is that helpful?
Yeah, thank you.
Yep. Okay, let's see, we've got, it looks like, oh, good question. Are we supposed to remove the incomplete runs? So let's see, do I have time? Yeah, I've got time. So interestingly, like I said, this was part of a data competition that was sponsored by the TRB Statistical Methods Committee. I tend to be very competitive by nature. And so while I did not win this specific competition, the group that won or the researcher that won, actually had a series of fundamental flaws in their analysis. So basically, they had very, very strong endogeneity, and they didn't realize it. I realized it because I had written that up in my paper, interestingly. And so the paper that won this data competition didn't actually get published in the special issue that was dedicated to it because they had an unaddressable concern that they really screwed up in their analysis. I bring that up because it's somewhat related to what we see here. So when we talk about incomplete runs, presumably we're talking about cases where you see missing values like the -1s and the 9999s and these various other cases. So I would not say that if we're going to exclude data, we need to make sure that there's a sound reason for doing so. And so in a few cases here, if we see a -1 for the first stop frame, that's not a particular concern to us because that simply means the vehicle didn't stop. They proceeded through the intersection, but no harm, no foul, as the case may be. Okay, and so those would be fine to include. Now, in this case, they're familiarization runs, so that was probably a bad example for me to use right there, but the same would hold in any other cases where we don't see that vehicle stop. Okay. We'll also see some cases where we see a -1 when that signal goes from red to green. And so the question there becomes then, is that problematic for us to include? And in this case, I would say no, it's fine to include this because we're only really concerned with the driver's response when that light is going from green to yellow. And so there's a number of cases where runs are truncated, where basically they're observing driver behavior, they clear the intersection, and then they're past the intersection before it turns back to green again, as an example. And you'll see a myriad of cases where you'd have some -1s. For that reason, likewise, for some of the other variables, we'd have some differences here as well. And so as an example, so maybe they didn't get to the stop line, which means they might have stopped in advance of the stop line, and then maybe the light cycled to red and that observation ended altogether. Okay. And so my guidance here would be as follows. If the run is truncated and you're not actually able to observe the complete event, or at least if there's something missing that would be impactful for your analysis, I would exclude it. But generally speaking, in most of these cases, there aren't problems with that truncation, generally speaking. There may be issues related to the truncation and some potential predictive variables of interest. I won't talk too much more about that because that's part of the investigation here. And it's very nuanced. Like I said, the person that won the paper competition didn't diagnose that issue. And so I'll stop talking there and just hopefully that has provided a sufficient answer to that question. Does anybody have any other questions about either the assignment, the project, or anything else course related?
Yeah, I kind of have a question about, I guess it's personally project related, but kind of course content. Anyways, so I'm trying to estimate some binary logistic and then multinomial models, and I'm having an issue with the models predicting like one of the categories because there's just a small amount of observations that observe that category. So I'm wondering if that's like omitted variable bias or something, and I guess what to do about that.
Okay, so great question. I'm somewhat remiss for not having brought that up previously, but the general rule of thumb there is it's no problem whatsoever. Well, in most cases, it doesn't represent any particular problem. What it's basically telling you is if we use just a simple classification scheme to try to guess or predict what category an individual is going to fall in, our model's not going to perform very well from that standpoint. But that's largely just a reflection of the data. Now, the one caveat I would give there is there are particular concerns that arise when you have very rare events, and there are actually some modifications that can be introduced in estimating these models because you may find some cases so let's say if you've got a data set and you have, let's say, values I've seen used in this setting would be like less than 10. So if you have less than 10 cases where that variable is equal to 1 or 0 or whatever the case may be there, you're going to have issues just with model tractability and just being able to converge to actual estimates for those parameters. But with that being said, that's not a necessary condition, and that still gives us useful information. So as an example, Jordan, in your case, if we're focusing on a binary outcome, and let's say the data are split 80-20, it's very conceivable your predictive model is not going to be, it's not going to have the explanatory power that you'd be able to correctly predict any of those 20% cases. Okay. But there would be value, your regression model would at least be able to give you some differences between individuals. So you could say, well, maybe this individual is 37% likely to be in that 20% case versus 5% likely to be in that case. And so that information is useful and valuable because our default estimation at the onset of the model is that none of those factors are useful to us. And our best guesstimate is just whatever those baseline probabilities are in our sample. So if it's an 80-20 split, we're just assuming 20% of the cases are going to fall in one category, 80 in the other category. But at a more aggregate level, we can think about our goodness of fit. So while we're not going to predict any individual observations to fall within those categories, if we average those probabilities across our sample, I would presume your model, as you add variables, is going to give better predictive performance just in terms of those changes in probability. So that probability might not get above 50%, or in the multinomial case, if you've got 5 outcomes, maybe it doesn't get above 20%, as an example, or whatever the maximum probability would be there. But it's definitely not a problem, and there's no error or concerns with the way that you've estimated your model. But that's a very good question. Does that answer it, Jordan?
Yeah, that helps. Thank you.
Okay. Any other questions? And I'd be happy. I mean, we could easily spend entire lecture periods just talking through some of the nuances of these different models and analyses you're working through, because the main objective of this course is that we've tried to design it such that it's very practice oriented and you're working with real data sets, because what you'll tend to find is that when you work with real data sets, some of the idealized conditions you often see in intro stat courses are not met, or there are some concerns that arise here. And so in my experience, the best way to learn it is to work with these different data sets and assess different types of regression frameworks and statistical analysis frameworks. And that kind of helps give you broader knowledge, because like I said, it's part art and part science, and you could give the same data set to 20 of the different top researchers in the field, and you're probably going to see different end results from at least several subsets of those researchers. Okay, so anyway, other questions or comments on anything course related?